Okay, so I think I want to zoom in a little, huh? That's too much. Maybe like that. And let's turn on the. Actually, I don't think we need the light, do we? Well, get a bit of a shadow with it. Okay. Okay, so yeah. And is this going to fit here? Um, maybe. Well, that's going the other way. All right, that seems to be all right. Uh, yeah. So I've improvised my phone as a docu-cam. It turns out this is possible. Um, so yeah, we were looking at an angle side situation. I think that was from the homework. Uh, and then we were introducing the ellipse and remind ourselves about how to graph ellipses. Then we looked at some examples from the exercises. So 11.3, and I think we briefly mentioned hyperbolae. Yeah, you can see we did introduce sorry, um, the idea of a hyperbola as being the difference of squares, right? And we draw the box, draw the asymptotes diagonally through the corners of the box, draw the vertices, and then sketch the hyperbola that fits that, right? And I guess that's 11.4, and 11.5 is shifted conics. So maybe let's go to the textbook, which I think I have available here. Yeah, and that's here, huh? Okay, and I think I'm in chapter 5. So let's go. I don't know. I was hoping to find a table of contents somewhere, but let's just go to page 700 and see what's there. We're in the section on. This is chapter 10. So maybe 730. Where's that? More matrices. 770. How about that? Guess and check. More matrices. Wow. Let's go to 800. Okay, so we're in this section on hyperbolas. That's just where I wanted to be. Okay, so we have the geometric definition of hyperbola. We showed how that would lead to the basic. Can we zoom out a little bit here? Yeah. So we see our hyperbola that is not shifted, right? And it's going to have a transverse axis of length 2a, right? Going from negative a to a, either on the horizontal or on the vertical, depending upon whether it's x squared over a squared minus y squared over b squared, or y squared over a squared minus x squared over b squared. Notice that a is always the vertex, either on the x-axis or the y-axis, right? And then the asymptotes go through the corners of the box, right? And if a is with x, it's like this one, a is with x, right? It's x squared over a squared. Then the asymptotes have slope plus or minus b over a. And we could show why that is, maybe. Let me see if I can justify that for you, because this is kind of a nice pre-calculus thing to do. So for that, we're going to go to the droid cam and get a little pencil and paper action. Okay, so let's say we have a hyperbola x squared over a squared. Is that visible? Okay. Let me make the mug cam a little smaller because that's not so essential. Mini me. Okay. So How are we doing? Question number 3 on my test doesn't have any variables, so I don't know how to complete it. How could we work on that? Okay, that was a private message, but I read it out loud publicly because I think maybe that's something that should be addressed right away. So let's put this on hold. Well, let me get started on this, or we can do this to finish the thought, and then we'll get to that. What we can do is say that this is equivalent to y squared over b squared equals x squared over a squared minus 1. So what did I do? I'll use the addition and subtraction properties of equality, right? And then I swapped the two sides. So I added this y squared term to both sides, or the opposite of it, right? And so I got y squared over b squared positive, and then I subtracted 1 from both sides, and then I swapped the sides. So I've got y squared on the left. That's basically why I swapped the sides. I want y over here. Now I'm going to multiply by b squared and divide by x squared, okay? And I'm going to say that's equivalent to y squared over x squared equals, I'm going to say b squared over a squared, right? Because I divided both sides by x squared and multiplied both sides by b squared. And then I divided both sides by x squared and multiplied, so there's going to be minus b squared over x squared. Oh, that's a little bit out of view there. So would you agree that's equivalent? So what happens as x gets large? And this is kind of calculus notation, but I think it's intuitive enough. So I'm going to say as the absolute value of x goes to infinity, b squared over x squared, b is fixed, right? So b is not changing. If x squared is growing without bound, this will go to 0, right? And so y squared over x squared, this ratio will go to b squared over a squared. That is to say that y over x will go to plus or minus b over a. And so that's a way of justifying that that the line y equal plus or minus b over a x are asymptotes for the hyperbola. Okay. Now let's put that on hold and go to the question at hand, which is question number 3 on the exam. Okay, let me see if I can bring that up so we can look at it. I think the exam is available. Oh, so this is week 14 still, huh? I meant to add a new module here. So we add a module for week 15. This is our last week of instruction. And we're going to finish up conics and review for final. Okay. So I'm going to add that module, and then I have to scroll down to the bottom and say, go to the top. Move module to the top, if you would please, if you'd be so kind. Now let's take some things from here. Oh, I guess I can't just drag it, huh? I have to say move it. Move to week 15, yes. How about the chapter 6 test? Let's move that to up here. And then, yeah, okay, so here's the chapter 6 test, and it was due today, yeah, before class. But maybe there's some questions about number 3. Apparently there is. So, yeah, oh, okay. Yeah. So AB is, yeah, there's no variables. So the degree measure of angle APB where we know that AB is the radius of the circle. So it only depends upon AB. It's going to be, well, let me draw the picture. So a little sidebar here. And somewhere I have a compass. So this is chapter 6 test number 3. And let's draw in the center of the circle is here. We can draw in a diameter, just for good measure. Now it says that AB is the radius of the circle. So that's this length here, right? So if I put my compass here and make a little mark there. Oh, crap. I need to put it back over here and make a mark back there, right? So this is AB. So it subtends a circular angle, right? So this is R, and this is R, and it subtends a circular angle. Let's put it back over here at the end of this diameter. It doesn't matter where it goes, right? It's going to be the same angle irrespective of where it goes, right? So what's the central angle that would subtend? And theta is defined to be, well, let's draw it here. The radian measure of an angle is the ratio arc length to radius, right? But if the arc length is the radius, AB, so it's the line segment AB, right? Yeah, huh. Okay, so this is an equilateral triangle, huh? So here's the center of the circle, right? So the distance from the center to a point on the circle is the radius. So every side of this triangle, OAB, is, oh, that's a terrible eraser. So this is equilateral, right? So that implies that the degree measure of angle AOB is 60 degrees, which if you multiply by pi over 180, you don't get the degree measure anymore. So let me put that in parentheses and I'll say radian. So I'm doing two things at once here, right? I'm getting the degree measure and the radian measure. So this is pi over 3, right? That's a well-known angle. And so we know that this is half of that, right? So this must be pi over 6. The arc pi over 3 subtends a circular angle of half of that, right? Pi over 3 over 2. The circular angle is half the central angle, which is pi over 6. So I think that's the right answer. There wasn't anywhere to put it in, right? There wasn't like a place to type it in, which I think maybe was a mistake on my part. But I did, for each problem, I put in one of these boxes, right? So you can describe what you're doing and or upload a file. Did that work out all right? Or
Professor, actually on the exam, a lot of us, like when we were taking it, when we put in the right answer the first time, it wouldn't give us full points. Like
oh,
the
really?
point system on every
Oh, yeah, yeah.
question.
That's because of these things. Which, yeah, when I read it, I mean, it's not going to be automatically graded properly, right? It's going to require me going in there and looking at your answers. And if you got the right answer, you're going to get full credit. But yeah, it's not going to show that automatically.
Okay.
Yeah, thanks for the observation. Okay. So I guess I would write here somewhere. Um, uh, Let O be the center of the circle, then OA equals OB equals R, the radius, right? Which is also stream of consciousness here, which is also AB. So triangle OAB is equilateral, meaning that, or can we say new sentence? Thus, we deduce that central angle AOB is pi over 3. And so the circular angle subtended by AB is half pi over 6. And I might take a picture of what I did here. Yeah. So if we go back, yeah, so oh, you couldn't see what I was writing. I didn't realize that. And this is very small, isn't it? Can we make it larger? Right. So what I wrote in here was let O be the center of the circle, then OA equals OB. I didn't draw that in here, right? Because I can't draw there. Is equilateral. I mean, I suppose I could if I still had my surface, but that was a disaster. We deduce that central angle AOB is pi over 3, 60 degrees, right? And so the circular angle subtended by AB is half that, pi over 6. I think that's right, yeah. So I could go back to my droid cam. What did we do to deserve all these droids? Now I kind of want to draw this one, this angle here, because that's the one where, so this is also pi over 6, right? But we know that these angles are equal because that's an isosceles triangle, right? And so whatever angle theta is here, this is going to be pi minus theta. And it's also pi minus these angles over here. Yeah, so each one of these are equal, right? So each one has got to be theta over 2, so that the sum of the interior angles of that triangle is 180 degrees. That's not a very good picture. I don't know. It's not looking very. Can I change the lighting here or the angle or something? Well, I guess it is what it is. I left my DocuCam in San Francisco, metaphorically. Okay. So yeah, thanks for that question. Any other questions on these? There's Santino. And what Snap is like a sharing, right? So yeah, so this is okay. I think I know what that is. I don't use that, so I'm not terribly familiar with it, but yeah. All righty, very good. Okay, so social media, right? Yeah, yeah. I'm sort of distantly aware that there is such a thing. Okay, let's go back to the text then. Yeah, and in the text, we see we can draw, right, so they're kind of justifying this slope of the tangent of the asymptotes the same way I did, right? So to sketch a hyperbola, there's a sort of a 4-step process, and I think that's largely what this chapter is about. So let's look at some of the exercises. Let's go with, say, steps of 12. So if we have x squared over 9, minus y squared over 65, psi an asymptote of the hyperbola. B, determine the length of the transverse axis. C, sketch a graph of the hyperbola. Okay, so let's do number 12. Just here. So this is 5.4, number 12. And we've got the equation x squared over 9 minus y squared over 64 equals 1. And so A is equal to 3 and B is equal to 8, right? We can just sort of pick that out from the equation. And the transverse axis is from, so we're on the x-axis, right? So it's from -3, 0 to 3, 0, and has length 6, which is twice A. Whoops, I guess I need to tilt it back when this happens. All right. And it would help to zoom in a little bit here. Okay. And what do they want? The foci? What are the foci? So I think it's C is the bigger one in this case, and it's going to be C squared equals A squared plus B squared. Is that right? Yeah. Not the same as the ellipse, right? It's sort of tantalizingly similar. I think on the ellipse, A squared is equal to well, let's see. I think it's a hypotenuse of some triangle, right? Let's see if we can see that. But that's going to be 73. So C is equal to the square root of 7. 8.2 maybe. I think it's closer to 8.2 than 8.1. Close enough, right? So then what do they say? So the vertices, where are the vertices? The vertices are at these points. These are the vertices. The vertices. Right, so the transverse axis connects the vertices. And what are the asymptotes? Well, so if it's a goes with x, then a is in the numerator, right? So it's, oh, sorry. No, a is in the denominator, right? It's when a goes with y that a is in the numerator. So the asymptotes here are y equals plus or minus, right? There's one that goes up to the right, one goes down to the right. And I think 8/3, is that right? Yeah. So these are lines with slope plus or minus 8/3 that go through the origin. Sorry, I'm going to have to scoot this up here again. All righty. And I think we're ready to draw a graph. Upside down. And so we want to get from -3 to +3, huh? So if we put the center there and say here's, yeah. And on the vertical axis, we want to get from -8 to +8, right? So let's make the scale a little bit smaller, half the size. So this is 6, 7, 8. So here's -8. Oh, and let's put perfectly evenly spaced hash marks going up as well, right? Okay. So so this is -3 here and +3. This is the x-axis, and that's the y-axis. And so what you want to do is draw the box, right? And the box has, A, B, negative. Oh, what happened? For some reason, I lost. Well, no, I didn't. Oh, I think Discord popped up is what happened. Not to worry, everything is fine. And so, got a point down here, and a point over here, huh? Okay, so this, this is the box. If you wanted to draw dash lines, they don't really help a lot. What you want are these diagonal lines, right? I think this is actually over a little bit further, huh? Yeah. So here's an asymptote. I'm going to make that a dashed line, I guess, through the origin, right? Because this is centered at the origin. And here's another one. Okay, and the vertices are here and here. Now, the focus is way out there. I didn't really leave room here to plot the focus, did I? Because they're on the x-axis, and this is 1, 2, 3, 4, 5, 6, 7. So it's going to be over here off the picture. So I guess I'm not going to be able to draw the foci in the graph. It's going to come down here, following the asymptote, pick up the vertex, and then come down here, getting closer and closer to the asymptote, right? Same thing on the other side. Coming off the asymptote, picking up the vertex, and then following the other asymptote out like that. So this length here is A, this length here is B, and this length here is C, right? So that's going to be the square root of 73. And if you were to slide that down, right, so that the top came down and there's like a ladder sliding out, it would pick up the focus, okay? you know, do you want to plot a point? So what if x equals 4, then you've got 16 ninths minus y squared over 64 equals 1. Take away, well, I'm going to say y squared over 64 is equal to 16 ninths minus 1, which is 7 ninths. And we could multiply both sides by 64 and take the square roots, right? So you'd have plus or minus, it's going to be 8/3 square root of 7. Is that off the, that's off the diagram, huh? Which means another little adjustment here, like so. Okay. Now square root of 7, who knows what that is? 2.6 something. Yeah. So let's say 2.65. I suppose I could get out a calculator, but 8 times 2.65 is 20. Yeah, 20/3. So that's about 6.9. Does that seem reasonable? So if we're here at 4 and we follow that up to the curve, we should be at about 7. Yeah. So yeah, you know, it's just because I didn't draw the curve carefully enough. We could do this in GeoGebra. So actually, how do you do this in GeoGebra? That's a good question. Let's jump over there and see. Do I have a GeoGebra? Yeah. Okay. So I want to bring that up here and say, yeah, so we have to write it as a function, right? Okay, so when we go to write it as a function, we want to solve for y. And we kind of went through that process, but let's go back to our sheet and see. Okay, so y squared over 64 is going to be x squared over 9 minus 1, right? Solving for the y term. And so then you can write y equals plus or minus. Well, I want to write it this way. 8/3 square root of x squared minus 9. Is that convincing? So you'd have to get a common denominator on the right side. So x squared over 9 minus 9 ninths, right? And then factor out the 1 over 9, multiply by 64. So you got 64 over 9 times the square root of x squared minus 9. When you take square roots, you get this, right? So let's enter in those in GeoGebra. So I've got positive 8/3 times the square root of x squared minus 9. Oh, looks pretty good, huh? So that's the upper half, right? We don't see any curve down below. We could scale this so we see, yeah, a little bit betterly. Let's plot in the asymptote 8/3 or 8x over 3. All right, that's an asymptote, it turns out. Also is negative 8 over 3, 8x over 3, right? So those are the two asymptotes. How do we get the bottom half of the curve? Well, that's just going to be the negative f of x, right? So there's the bottom half of the curve. And let's zoom out a bit, okay? As we zoom out, we see, yeah, it certainly is approaching the asymptotes, right? Oh, it's like all dressed up for Christmas. All right. Yeah. Should we plot the asymptotes? So we've got the point 8 square root of 7 over 3. And y is 0, right? So there's an asymptote. And I don't know, can we plot negative a? Is that a thing? Yeah, there it is on the other side. And if x is 4, then what is f of x? Oh, f of 4. And we said, I said 6.9. Turns out to be a little bit bigger, 7.06. Yeah. And you also have the negation of that, right? Which would be the point x coordinate is 4 and negative f of 4, right? It's down there. I don't know why we're interested in that point. It's just to, pick a point out of a hat and plot it on the curve. Okay, so as we zoom in here, yeah, actually, it's pretty well behaved, right? It doesn't freak out too much near. Just wondering, what if we were to zoom in just vertically? Yeah, that doesn't look too bad. Okay. But let me show you another way of plotting this, which is to use the parameterization of it. Okay. So this would be pencil and paper again. And I think we need a new sheet of paper for this. Okay, I'm going to have to. There we go. Okay, so remember the identity, cosine squared theta plus sine squared theta equals 1. And we use that to parameterize an ellipse, which I'll remind you about that in a bit. But let's take a slightly different approach. If we divide all three terms by cosine squared, we get an alternate version of this, right? So divide both sides, each term on both sides of the equation by cosine squared. This is going to be 1. This is tangent squared. Sine over cosine is tangent, so this is tangent squared. And that's equal to secant squared theta, right? So an equivalent form of that is to say that secant squared theta minus tangent squared theta is equal to 1. So that's a difference of squares equals 1, right? So that's like the hyperbola. The ellipse is a sum of squares equals 1. The hyperbola is a difference of squares equals 1. And we can use this form of the Pythagorean identity to say, yeah, well, if this is x squared over 9, and this is y squared over 64 equals 1, then we can just match these things, right? We can say x squared over 9 is secant squared, and y squared over 64 is tangent squared. So let's do that. So x squared over 9 equals secant squared theta. That's going to say that x is plus or minus 3 secant theta. Similarly, y squared over 64, am I still, no. Y squared over 64 equals tangent squared theta. Implies that y is plus or minus 8 tangent theta. We might as well just take the plus, right? So now we have x as a function of theta and y as a function of theta. Is GeoGebra able to handle that? Well, let's take a look, see. So I'm just going to basically go over here and say, choose all and delete. Sorry, all gone. So now I'm going to use a keyword curve. And Do you see? You don't see what I see. Okay, yeah, there's a little pop-up window that comes when you start typing curve. It says, well, which template for curve do you want? And I want this third one here. So I chose a template from a menu here. And curve, so what this says is, express x as a function of some parameter, let's say t. I'm going to use t instead of theta, okay? And express y, so that's this one, right? So I'm going to say that's 3 times secant of t. T is going to be my parameter instead of theta. All right, then I go over to the next thing. That's express y as a function of, I didn't put in the time sign, but I think that's fine. Now it says, what's your parameter? I'm going to say that's t. By the way, I'm hitting tab to sort of go back and forth here. And so that's sort of a quick way to enter in these things, right? So what the next two things it wants to know is, so it's got an expression for, y, right? An expression for x in terms of the parameter t. Then it wants to know, okay, what is the parameter? Well, it's t, I said so. And then what range of values you want to choose for t? Well, I could go, t goes from 0 to 2 pi. And this is what I get, which is that hyperbola, right? It's a little bit more than that hyperbola though, right? What are these lines in between here? Well, those are the asymptotes. Why does it draw the asymptotes? Well, that's sort of an artifact of how it draws, right? It doesn't actually draw every point on the curve because there are infinitely many points and a computer is a finite machine. So it simulates that by drawing points which are pretty close together and then connecting them with a straight line. But when it gets out to the end of the asymptote here, out here, does it go forever? Or does it? Yeah, see, it stops. Why? The asymptote actually goes on forever. Well, the reason it stops is because it's a finite machine and it's taking regular increments in x, or sorry, regular increments in t, the parameter, right? And so the next increment in t took it across the asymptote. So, but it actually draws the asymptote because it's going to, the next point it's going to pick up is over here, right? So that's actually not a perfect asymptote, because it's actually connecting points that are on the hyperbola that are very close to the asymptote. And so for all intents and purposes, it looks just like the asymptote. But we could limit t. Should we limit t to some other interval? Let's see, what can I do here? I can say, suppose we're just going to pi over 2. That would be 1/4, right? So we just get this branch then, right? And at t equals 0, we're going to start out here. If t equals 0, the secant of 0 is 1, right? It's the reciprocal of cosine. Cosine of 0 is 1. Secant is the reciprocal of cosine. So 3 times 1, x is 3. So it's starting there, and tangent of 0 is 0. So it's starting where x equals 3 and y equals 0. And then as t increases, secant increases, right? Cosine decreases, but secant is the reciprocal of that decreasing quantity. So it's increasing. And tangent is also increasing. So both x and y increase, and they approach the line y equals 8/3, is it, asymptotically? And we could like copy this over. Is that possible? Just do the Control C. Oh. Huh. Yeah. That's interesting. Actually, okay. That's odd. Okay, so apparently all you have to do is draw the pair of points, right? But if I say curve, And then I can limit my parameter to t and going from pi over 2 to pi. Yeah. So what's going on here? Well, as we cross the asymptote, we end up over here. Well, somewhere over here. It actually, I'd say it's going out a little farther because it's a shorter interval. So, wow, you got to go way out here to get to the